Okay, welcome to part 2 of this Earth to Mars series that I'm trying to put together. And in this video, in this section, in this part, I want to talk about the good day or a good date to get to Mars so we can see, kind of how much difference it makes. And in this one, I'm going to use the same date that NASA used to launch the Curiosity rover out to Mars, and that was November 26th, 2011. Now, on that topic of picking a good date to get to Mars, there are several resources you can use, probably a half dozen or maybe even many more than that. There's a website called the Cosmic Train Schedule. I'll put a link to that in my description box. There's a couple of tools on Orbit Hangar that you can use. One of them is called the Trajectory Planner, and there's another one called the Trajectory Optimization Tool. So if you want to use those to help you find better dates to get to Mars, then of course you can use those as well. Let's get into it here. And let's just kind of go through the same process as before, where we bring up TransX and we try to find a good solution for getting to Mars. So we have TransX loaded over here, and we'll do most of the work here on this side where we have the nice larger view. And in the interest of time, I'm going to go through this even more quickly than I did in the first part, trusting that if you need more, step by step, then you can always refer back to that other video. So again, plus over to escape, forward, select Mars. And it's one thing I will point out here, whenever you're making a trip to Mars, if you look at your TransX MFD, notice the alignment of Earth as compared to Mars, and it will always look about like this if you want to use this type of low energy approach to get out to Mars. Earth will always be behind Mars in its orbit by I don't know whatever that is, an eighth of an orbit or something. I'm not that great at doing fractions off the top of my head, but you get the idea. Earth is orbiting the sun this way, Mars is orbiting the sun this way, so Earth is behind Mars by about that much. And no matter what date you pick, in 18-month intervals approximately, the Earth should always be behind Mars by about that much in order to get that ideal alignment. Okay, so let's go ahead and go through this. Eject plan, we'll add in the amount of prograde velocity that we need. Again, watching the closest approach. Go to a finer setting. Now I'm going to come down here, get this over to view encounter so I can be prepared to be keeping an eye on that here in a moment. Get the closest approach as low as we can for now. About right there. Again, back over to change plane, and we'll try positive first. And I'm going to say that's the wrong direction, so we'll go negative. That looks better. And got that about lined up, so back to prograde. And you'll notice, let me point something out. When you get the closest approach down to a certain point, if you've got view encounter already on, you'll notice like this green line pops into view and you get some more information. So that's one reason to keep that view encounter up on the other side. And again, once you get down to a much lower number, then you want to look at the minimum altitude instead of the closest approach over here, because that's just the rough estimate. So go to a finer setting, and it's going up, so we go back the other way for a moment. Go back to the change plane. Prograde. Go to a finer setting. Prograde. Change plane. I like to do most of the dialing in with change plane and prograde, and then if necessary I'll add some outward into the mix. But usually I find I can get where I need to be just with prograde and change plane. Okay. See, now we're getting a shape there. Getting in pretty close. We're down to 2,000 kilometers. So we'll go to some finer settings. Okay, now we'll go to prograde. And go to hyper setting. Okay, there we have it. We have a minimum altitude at Mars of just 233 kilometers. And again, I hate to sound like a broken record, but this, of course, will not be our final altitude by the time we get to Mars because of just things that change in the math models, all that. But nevertheless, this gives us a good starting point. So let's compare what we have here with what we had before. In this scenario where we're leaving Earth on a good day for approach to Mars, our prograde velocity that we're going to require to get to Mars is 2.869 K, whereas before it was 5.395 K. So before it was almost twice as much. We were using almost twice as much fuel just to get out to Mars by going at the wrong time. And our encounter velocity this time is 3.9, whereas before it was 7.3. So again, before it was almost twice as much. And that's important because the encounter velocity, when you reach Mars, you've got to do something with all that energy. So if we're approaching Mars at a really, really high speed, then it's going to require a tremendous amount of fuel to get rid of that energy, or it's going to require a really dangerous aerobraking maneuver to get rid of all that energy. So we want to use a little bit of fuel to get out there, as little as possible, and we want to approach Mars, at a fairly slow rate, if possible. That way we minimize the amount of fuel that is needed once we get to the other end. And we can also see that the amount of time that it takes us. Just one moment, let's do our subtraction again. 56247 is the date that we'll get there, minus this date, 55891. So this time it's going to take us 356 days, so a little over 1 year, and not quite 1 year, to get to Mars using this solution. And if we wanted to speed that up a little bit, we could do that, because obviously Curiosity left on November 26, 2011 and got there in August, so we could speed that up a little bit by adding a little bit of outward velocity, either positive or negative. I'm not completely sure which direction I'd have to go with it, but that would be one way to ensure that we could get to Mars in the same time frame that NASA did with the Curiosity rover. So that's that part of the setup, and this is a pretty good plan. This is what I'll ultimately end up using, but there's still some more work to be done. Now we need to go back to stage 1, and we have a little bit of work to do here. And don't be intimidated by all this crazy looking stuff. It's really not all that difficult. The first thing we need to do here is, actually the first thing we're going to do is come over here to View Setup, and we're going to go to the graph projection. It's set to ecliptic by default, and I find that it works better if you have it on plan. It just makes all this easier. So then we'll come back over here to View Escape Plan, and the first thing I want to do is this PE distance. If you remember, if you happen to see my other Earth to Mars video, you remember that I said that this is the distance above the Earth's center that we're ultimately going to be orbiting at. So if the distance between the Earth's center and the surface is this number, then we just want to add 200 kilometers to this number in order to set our PE distance. So that would be 6.571, because 200 plus 371 is 571. So 6.571 will be the PE distance that we'll use here. Do the adjustments as necessary. Okay, now that has our PE distance set. So that says when we take off, we want to have an initial orbital altitude, a target of 200 kilometers, and I find that that's a pretty good number. The next thing I've got to do is go through the variables to get to the eject orientation. Now the eject orientation, it's a little difficult to wrap your head around, and I am not going to pretend that I completely understand what the eject orientation means. I feel like at this point I've got a pretty good idea, but it would be difficult for me to put it into words. Fortunately, you don't have to understand exactly what it is or how it works in order to be able to set this up. In short, all you've got to do is adjust the eject orientation so that this long white line lays straight over top of this green line. But there's a caveat, and I'll get to that in a moment. Let's say you go this way with it. So you add in a bunch of positive eject orientation, and voila, we have it here. We see that the white line is laying straight down over top the middle of this green ellipse. And by the way, this green ellipse is basically our orbit around the Earth, but since we're sitting here on the ground and we haven't gone anywhere yet, that's why it appears basically as a still green line that isn't moving. So we've got the eject orientation set, but it says here that when we take off and get into orbit, our initial heading would be 302 degrees. Well, 360 degrees, or 0, is straight north, and 270 is straight west. So a heading of 302 degrees means that we're going to be flying northwest when we take off and try to get into orbit. And you can actually do that, but the problem is you'll be fighting against the rotation of the Earth, and you'll use more fuel to do it that way. And when we're, everything in space is all about being conservative with the fuel, so we don't want to do that. We would prefer to take off and head east so that we are not fighting against the rotation of the Earth. So all we have to do then is just continue clicking ++ and swing that around in the other direction. Pretty simple. Do an adjustment there because I can see it's a little bit off, and there it's lined up really well. Now this says that I will have a heading of 121.9, which we'll call that basically 122 degrees. Now that's not straight east, but it's better than going, north and west. Now there is something I do want to talk about with regards to this eject orientation. So I have this plan set up, so what I'm going to do is close that out and then press Control S to quick save this scenario as it is. And then I'm going to pick up this video in the next part where I want to talk a little bit more about this idea of the eject orientation. Notice that in this scenario I'm at Wide Awake International. And one thing I'll point out quickly is where Wide Awake International is at. So if we look here at Earth, you can see Wide Awake International is close to 0 latitude. So that's just something to keep in mind. So I'm going to go ahead and stop this video at this point, pick it up in the next one where I want to continue a little bit more about this topic of the eject orientation. Okay, welcome to part 2 of this Earth to Mars series that I'm trying to put together. And in this video, in this section, in this part, I want to talk about the good day or a good date to get to Mars, so we can see kind of how much difference it makes. And in this one I'm going to use the same date that NASA used to launch the Select Mars. And it's one thing I will point out here: whenever you're making a trip to Mars, if you look at your TransX MFD, notice the alignment of Earth as compared to Mars, and it will always look about like this if you want to use this type of low energy the Curiosity rover out to Mars. And that was November 26th, 2011. Now on that topic of picking a good date to get to Mars, there are several resources you can use, probably a half dozen or maybe even many more than that. There's a website called the Cosmic Train Schedule. I'll put a link to that in my description box. There's a couple of tools on Orbit Hangar that you can use. One of them is called the Trajectory Planner, and so you have TransX loaded over here, and we'll do most of the work here on this side where we have the nice larger view. And in the interest of time, I'm going to go through this even more quickly than I did in the first part, trusting that if you need more step by step, then you can always refer back to that other video. So again, plus over to escape, forward, and there's another one called the Trajectory Optimization Tool. So if you want to use those to help you find better dates to get to Mars, then of course you can use those as well. Let's get into it here. And let's just kind of go through the same process as before, where we bring up TransX and we try to find a good solution for getting to Mars.